lecture, we described stiffness and compliance tensors. Now we will discuss wave equations. Here is the plan for this portion of the lecture. We will start by describing the wave motion using the Newton law. That is, force equals mass multiplied by acceleration. The mass in this equation will allow us to introduce the notion of mass density. We will then connect the wave motion with P and S waves, including P and S-Wave velocities. We will then review the various ways of characterizing isotropic linearly elastic rock formations. We start with the equations that govern this wave propagation, which are derived from Newton's equation of motion. We have two equations: Newton's equation of motion, which is related to density, and Hooke's law, which is related to resistance to deformation. We will combine the two later on in this lecture. Newton's equation of motion states that force equals mass times acceleration for each particle at a given time. That is why our analysis here will focus on a particle which we will represent by an elementary volume. Let's repeat this. This is a very important point. Newton's equation of motion states that force equals mass times acceleration for each particle at a given time. That is why our analysis here will focus on a particle which we will represent by an elementary volume. In the previous lecture, we derived the particle acceleration as the second derivative of particle displacement with respect to time. Our next task is to derive the force acting on each particle at any given time in order to obtain the equation of motion. The force, which is a vector, acting on each particle is obviously a function of stresses on this particle. A force is a three-component vector, that is, a tensor of rank 1, whereas stresses form a tensor of rank 2, that is, a 3x3 matrix. So we have to somehow capture many stresses in each component of force. Let's define the x component of this force, that is Fx. This figure shows an element volume and illustration of stress component in the x direction, on opposite faces of the elementary volume illustrated here. So the force Fx depends on tau xx, tau yx, and tau zx, as illustrated here. For the contribution of tau xx to the x component of this force, that is Fx, we consider the stresses on the faces A, B, C, D, and E, F, G, H. The net stress in the x direction acting on these two faces is given by this difference, which is the stress on the face E, F, G, H minus the stress on the face A, B, C, D. The resulting force is the stress multiplied by the surface area on which it acts, because Fx is not a surface force, but a body force. For the contribution of tau xy to the x component of this force, that is Fx, we consider the stresses on the faces A, D, H, E, and B, C, G, F. The net stress in the x direction acting on these two faces is the difference, which is the stress on the face B, C, G, F minus the stress on the face A, D, H, E. Again, the resulting force is the stress multiplied by the surface area on which it acts, because Fx is not a surface force, but a body force. For the contribution tau xz to the x component of this force, that is Fx, we consider the stresses on the faces A, B, F, E, and D, C, G, H. The net stress in the x direction acting on these two faces is the difference, which is the stress on the face D, C, G, H minus the stress on the face A, B, F, E. The resulting force is the stress multiplied by the surface area on which it acts, because Fx is not a surface force, but a body force. Now we're going to sum all three contributions to the force in the x direction to obtain the total force in the x direction. Now we can apply the Newton law of motion in the x direction. That is, total force in the x direction is equal to mass multiplied by acceleration. So we have the equation of wave motion in the x direction. Similar considerations of stresses in the y and z directions lead to force components in the y and z directions, and then we obtain the equation of motion in all three directions. That is x, y, and z by using again the formula force equals mass multiplied by acceleration. These equations of wave motion are valid for whatever stress-strain relations hold, including cases in which the medium is inelastic or anisotropic. In other words, the behavior of material does not explicitly enter into the equations of motion. We will discuss these cases in future lectures. In this lecture, we have limited our discussion to isotropic elastic cases. So we have two equations: Newton's law, which includes mass density, and Hooke's law, which includes stiffnesses. By substituting Hooke's law into the equations of wave motion, we obtain the following, which is known as the elastodynamic wave equation. Note that this wave equation has three terms. The first term describes the mass density multiplied by acceleration. The second term describes the gradients of stresses, in other words, forces. And the third term is zero. This elastodynamic wave equation is generally characterized as homogeneous because it does not include seismic sources. We will discuss the introduction of seismic sources later. The variables are explicit in these equations in order to emphasize that the density and the stiffness tensor are independent of time under the assumption that the medium is linearly elastic. With this assumption, the subsurface can be characterized by stiffness constants and density. Notice that in addition to stiffnesses, we have introduced another characteristic of rock formation, namely the mass density, also simply called density. In sedimentary rocks, the density varies between 1.8 grams per cubic centimeter and 2.6 grams per cubic centimeter. Now it's time for a quiz. Rewrite the elastodynamic wave equation for non-viscous fluids. The answer to the question posed in the previous slide is as follows. We simply have to use the fact that tau ij is equal to negative pressure times the Kronecker delta ij, and the stiffnesses reduces to the bulk modulus only. Here's the second quiz. Rewrite the elastodynamic wave equation for a homogeneous, isotropic, linearly elastic medium using the del vector symbol. Here is a reminder of the del vector. Here is our answer. We obtained this answer by using the stiffness tensor Cijkl for isotropic media, and by assuming that the Lemay parameters are independent of position, or particles. Note that we are going to use this solution for the remaining portion of this lecture, so please pay close attention. Now we are going to connect the elastodynamic wave equations with P and S waves, including P and S-Wave velocities. Our objective in this section is to introduce the important notions for describing wave propagation in homogeneous isotropic elastic media. Scalar potential, which is another way of introducing P waves, and vector potential, which is another way of introducing S waves. P and S wave velocities, SV and SH motions. The elastodynamic wave equation of motion for homogeneous isotropic linear elastic media obtained in the previous quiz can be rewritten to highlight the volumetric deformations, that is, P wave, and the change of shape through shear strain, that is, S wave. These two features are clearly visible in this form of the elastodynamic equation for homogeneous isotropic linearly elastic media. Note that we use the identity in the bottom here to turn the elastodynamic equation that we derived in the second quiz in this form. Notice that the divergence of particle displacement describes the volume strain, whereas the curl of the particle displacement describes the change of shape. This equation is one of the most complicated differential equations in classical physics. Further insight into the structure of this equation is obtained by introducing the Helmholtz decomposition of the particle displacement into scalar and vector potentials. The Helmholtz decomposition of a vector field states that any arbitrary vector field can generally be represented as a sum of curl-free and divergence-free forms. The Helmholtz decomposition of the elastic displacement field is given as a gradient of the scalar potential plus the curl of the vector potential. So the gradient term is curl-free. That is, it does not include change of shape. And the curl term is divergence-free. That is, it does not include volumetric change. In other words, substituting the Helmholtz decomposition into the elastodynamic equation allows us to split the elastodynamic equation into two equations. One equation for the scalar potential, that is for P wave, and one equation for the vector potential, that is for S wave. This equation is the wave equation for the scalar potential, known as the P wave displacement. The key parameter here is the P wave velocity, Vp. That is the speed at which the P wave propagates. In other words, this equation allows us to introduce the P wave velocity and defines it as a function of Lemay's parameters. For this solution, there is no twisting of the medium, only stretching and squeezing. Let's watch. The deformation, or a temporary elastic disturbance, propagates. Particle motion consists of alternating stretching and squeezing. Particle motion is parallel to the direction of propagation, that is, longitudinal. Material returns to its original shape after the wave passes. The motion vector is parallel to the direction of propagation, as illustrated here. Again, for this solution, there is no twisting of the medium, only stretching and squeezing. This equation is the wave equation for the vector potential, known as the S-wave displacement potential. The key parameter here is the S-wave velocity, Vs. That is the speed at which the S-wave propagates. In other words, this equation allows us to introduce the S-wave velocity and defines it as a function of Lemay's parameters. The vector wave equation can alternatively be written in the standard wave equation form. This form is often useful when we seek one-component solutions for the vector potential. For S-wave propagation, the displacement can have any direction in the plane normal to the directions of wave propagation. Let's watch. Particle motion consists of alternating transverse motion. particle motion is perpendicular to the direction of propagation, that is, transverse. The transverse particle motion shown here is vertical, but can be in any direction. Let's repeat that due to its importance. Particle motion consists of alternating transverse motion. Particle motion is perpendicular to the direction of propagation, that is, transverse. The transverse particle motion shown here is vertical, but can be in any direction. An elastic medium in which the properties change in the vertical direction only, that is, a vertically inhomogeneous medium. We normally choose the xz plane to contain the direction of wave propagation. And we consider two motions. One motion is in the xz plane, which contains the direction for the wave propagations, and the other motion is normal to the xz plane. Shear wave motions in the xz plane are called vertically polarized, or SV, and shear waves normal to the xz plane are characterized as horizontally polarized, or SH. This decomposition of S wave into SV and SH is the result of the fact that S waves are described by the vector potential. SH and SV motions are illustrated here. S waves have a particle motion orthogonal to the direction of wave propagation. S wave particle motion is polarized in two directions, one horizontal at the top and one vertical at the bottom. Assuming 2D wave propagation, we may write SV wave in terms of particle displacement in the x and z directions, or as wave equations based on the y component of the potential vector. Because we are in the xz plane, the derivatives of the component of the potential vector in the y direction are assumed to be 0. So we end up with the following wave equations, which involve only the y component of the vector potential. Assuming 2D wave propagation, we may write SH wave in terms of particle displacement in the y directions only, or as wave equations based on the x and z components of the potential vector. Because we are normal to the xz plane, only the y components of the displacement is involved in the wave equation. To summarize, in vertically inhomogeneous elastic media, P and SV waves, which both have polarizations in the xz plane, may couple at layer interfaces. SH waves, which have a different polarization normal to the xz plane, do not interact with P and SV waves. Thus, SH motion separates from the coupled PSV wave in this case. Observe that the scalar and vector potentials of the displacement field serve to uncouple the elastodynamic wave equation into two wave equations, with waves traveling with distinct wave velocities, Vp and Vs. Let's repeat this. This is important. Observe that the scalar and vector potentials of the displacement field serve to uncouple the elastodynamic wave equation into two-wave equations, with waves traveling with distinct velocities, Vp and Vs. Again, these two waves travel with different velocities. Note that the uncoupling into two-wave equations holds only in an infinite homogeneous medium. P and S-wave motions are independent. If the motion begins as a P wave, it will continue to be a P wave. If it begins as an S wave, it will remain an S wave, as we pointed out through the movies of wave propagations in one of the first lectures of the 200 level. However, when interfaces or scatterers are present, we will see in future lectures that boundary conditions in general generate a coupling between P and S waves. That is, the boundary conditions give rise to the phenomena of mode conversion. Note that Vp is greater than Vs, as you can see from this equation. Remember that the Lemay parameters are positive, and the density is also positive for materials found in nature. Note also that if the medium is a non-viscous fluid, then Vs equals 0, and Vp is the speed of waves in the fluid. S waves cannot propagate in non-viscous fluids. We now review the various ways of characterizing isotropic, linearly elastic rock formations. In isotropic elastic rock formations, the wave equation and the constitutive equation, which govern wave propagation, contains three characteristics of rock: density of mass and Lemay's parameters. That is, lambda, mu, and rho. Other choices with more physical meaning are generally adopted in seismology. Bulk modulus, shear modulus, and density is one classical choice. P wave velocity, S wave velocity, and density is another choice. P wave impedance, S wave impedance, and density is quite a popular choice for reasons that will become obvious in one of the future lectures on energy partitioning at an interface between rock formations. P wave velocity, the Poisson ratio, and density is another choice. Let's elaborate on Poisson's ratio, which we introduced in the previous lecture. Poisson ratio can be determined from measurements of the shear and compressional velocities. In a fluid, the S-wave velocity is 0. The Poisson's ratio in this case is 0.5. For solid rock formations, the Poisson ratio is smaller, between 0.2 and 0.35 for most consolidated rocks, and between 0.4 and 0.45 for unconsolidated materials, but always positive. The fact that Poisson's ratio is always positive implies that P wave velocity is always greater than S wave velocity times the square root of 2. We've arrived here at a very important result. P wave velocity is always greater than S wave velocity, with the extra precision that P wave velocity is actually greater than S wave velocity multiplied by 1.4. This result is only valid for isotropic rock formations. Again, S-wave does not propagate in the fluid, so shear modulus is 0, or S-wave velocity is 0. So the fluid can be characterized by bulk modulus and density, or P-wave velocity and density. In this case, the P-wave velocity is called acoustic velocity. Or it can be characterized by P-wave impedance and density. In this case, the P-wave impedance is called acoustic impedance. Here we illustrate examples of P-wave velocities, Poisson's ratio, and VP-VS ratio for various lithologies. This is a useful diagram for connecting the parameter we just described with lithology rock formations. Here is an exercise about two basic materials which dominate our environment, air and water. So what is the density of water? What is the velocity of water? What is the velocity of air? And finally, what is the density of air? We have now concluded our description of wave equations. When we return, we will describe external force sources. Thank you very much for your attention.